So before we get going too far, I want to throw up this service announcement just so people know that I think this is fascinating stuff, but technically this is not stuff we're covering this semester. We just happen to have enough of time that we can squeeze it in. And I think it serves as a great sort of refresher of like, hey, you know, there's something going on here that we learned a long time ago in a different setting, and it translates over really nicely. So what we're talking about today is non-homogeneous ODE systems. Now, if you remember what we mean by non-homogeneous, is there was sort of this extra part floating around. So the non-homogeneous refers to this f of t part. So there's this extra piece there. And we learned how to handle non-homogeneous systems before, or really I shouldn't say non-homogeneous systems, but non-homogeneous differential equations. And it came down to saying, well, there's two general approaches, namely method of undetermined coefficients and the method of variation of parameters. Now, it turns out that both these ideas have this nice translation. And hopefully by the end of today, you should feel like there's a certain sense of deja vu. It's like, oh, you know, some of the same things we talked about before translate over into our new setting. So in other words, the same things we were doing when we just had normal differential equations feel and act in this new environment where we have systems of differential equations. It's all about notation. And so in some sense, the hardest part in the last couple of weeks has been saying, well, what do we mean by matrices? What are they? How do we work with them? Okay, so we're starting with the method of undetermined coefficients. And there is some limitation to this method in that it works when f of t has certain form. So when do we use it? Well, if you think back to undetermined coefficients before, we said, well, there's certain parts of the function that we want. Some combinations of things that look like a power of t times maybe an exponential function. Could just be a power of t, because the exponential function could be e to the 0. Or maybe there's a sine or a cosine attached. Now you'll notice there's these little extra pieces here, and these represent just vectors u. So these little pieces here are saying, well, we have some function times a vector u. And before, instead of a vector, we'd have a constant, a number in front. So okay, so suppose f of t is a linear combination of things that look like that. Then we say, all right, let's run the procedure like we would before. Now, to recall the procedure before, the idea was to say, you know, we can make a good guess. Not really just a good guess, but we know our solution has to have a certain shape, a certain form. The only thing we don't know is some coefficients. So we say, okay, our solution for our particular function xb looks like something up to some undetermined coefficients. And then we said, okay, once we had that, we would feed it into our differential equation and say, all right, now let's figure out what the coefficients have to be in order for everything to sort of balance out on both sides. It turns out the same idea works. The only difference is now, instead of saying undetermined numbers that go in front of our functions, we have vectors. That's the big change. So it's now, we can think about our undetermined coefficients as undetermined vector coefficients or something like that. But other than that, the process is the same. Well, there is one small catch. There's a little thing here. The only difference, well, we used to have things where we do a bump. Things that go bump in differential equations. And the bumps are a little different now. Sometimes it'll happen, you don't actually need the bump, but you don't know that a priori. And the other thing that can happen is if you think about how bumps worked before, you said, well, I have to bump out of the homogeneous part. And it's going to be slightly different. Okay, and I think perhaps when we come to an example, we'll point out why. So let's just jump into a quick example. So give the form for the particular solution. Notice it doesn't say find the particular solution, just give the form. And our differential equation is x prime equals this matrix, 4, 2, 3, minus 1, x, plus this part here. So this part on the end, this is our f of t. All right. So before we get too far into this process, it might just help to think of some of the things we would do before. And one of the things we would do when we were doing method of undetermined coefficients before was we'd say, well, let's look at the homogeneous part. And for us, it comes down to saying, let's think about this matrix. And we'll test your recall, because we've seen this matrix before. 4, 2, 3, negative 1. Do you remember anything about this matrix? And by anything, the eigenvalues. What? 5, negative 2. All right. Someone either is really good at computing eigenvalues or they know how to write things down. Both good skills to have. All right. So we have the eigenvalues for this matrix are 5, negative 2, which means that we have solutions in the homogeneous part, e to the 5t times some vector. I don't worry about what the vector is right now, and e to the minus 2t times some vector. All right, we'll come back to that in a second. All right, now the first issue is we look at this and say, is this something where we can use the method of undetermined coefficients on? Because right now, f of t just looks not like a linear combination of anything. It just looks like a big, like, wow! Can we use the method of undetermined coefficients here? Or is there something we should do first? Linear combination means what? Like we can add. And so here, one of the things we can do is we could say, you know, just because it's not written in the way I want, maybe I can rewrite it. And linear combination says, let's pull things apart. Now, the nice thing is when we're dealing with matrices, vectors, they work great with addition. Very easy to pull things apart. Very easy. All right, so let's think about some functions that we see inside f of t, and let's pull it apart into our pieces. So what are some functions we see inside of f of t floating around? Sorry, what? Okay, we see a t. Okay, so what we can do is you can say, well, let's pull the t part out. So if I pull t out, what do I have here as a vector? Or if you want, we'll come back and fill it in later. What are some other functions? Maybe we'll fill out our other functions. There's t e to the 5t. There's t squared e to the 5t. Somebody mentioned, what else? There's sine of t. Is there anything else? So there's actually this phi, which doesn't fit into any of these categories. We can think of that as being just associated with the function 1. So let's fill in the vectors. So t, what's attached to the t's in the top and to the bottom? 3, negative 2. All right, how about t e to the 5t? 0, 7. T squared? 1, 0. Sine t? 1, 0. And the 1? 0, 5. And so now what we have is that we see, okay, so f of t is this combination of these functions, all those functions fall into our category, times appropriate vectors. Now, in terms of setting up the method of undetermined coefficients, we don't really care about these vectors. We just care that they are there. So if we were put on our old hat, so we go in and we say, okay, we're going to put on what we learned before we talked about systems hat. What we would do at this point is we'd look at the functions in the front. And we'd say, okay, what are the important functions that we have to have as part of our solution? So what would the functions be that we need to have as part of our solution? Well, we'd need 1. What else would we need? T. Sorry, what? So we need t e to the 5t, but if we included t e to the 5t, what else would we need to include? We'd have to go down e to the 5t. What else do we need to have? T squared e to the 5t, but if we include that, we need to also include t e to the 5t and e to the 5t, but we already have those, good. What else? Sine of t. But the rule is, if you include sine, what needs to go in? Cosine, right. That's method of undetermined coefficients. Okay. Now, that's without taking into account the bump. Remember, we should check. Does anything overlap? Well, do we have any overlap going on? Yeah, e to the 5t overlap. So, what we would do is we'd say, okay, everything which had e to the 5t, we would do what to? Multiply by t. So we'd have t squared, t and t cubed. And then we'd cover this up. So that would be what we would do before. So here is the difference. Now we keep that in. And you might say, why do we keep it in? And before, why did we take it out? The reason we took it out before is it truly was redundant, because you'd have a constant e to the 5t, and that goes into the homogeneous part. But now remember that we don't have constants, we have vectors. And I can change a vector so that it's still some vector times e to the 5t, but it's not part of the homogeneous solution. And that's why we have to include it. There's a subtlety between numbers versus vectors. All right. Well, that says these are the pieces, the functions that have to go into the little slots here. So there's 1, 2, 3, 4, 5, 6, 7, 8. 8 functions. And then now, each one of those gets a vector. So, we say that our particular solution, xp of t, will be 1 times some vector ab plus t times some vector cd. I'll do the e to the 5t's in order. So plus e to the 5t, some vector capital E, capital F, t e to the 5t, gh, t squared e to the 5t, ij, t cubed e to the 5t, kl. And now we're down to the last two. Sine of t, mn, and cosine of t, I'll skip, p looks too much like 0, pq. Sorry, O, 0 and O look too similar. And so, that's our particular solution. So we know our particular solution that helps us satisfy that piece looks like this. And we only have to figure out A through Q. But we skipped O, so that saves us one letter. And how would we figure it out? Plug it in. Take the derivative. And the nice thing is you only ever have to take first derivatives because we only deal with first order systems. So we never have to deal with higher derivatives. Take the derivative. Take A times that. Add f of t, so it really means add these pieces in. And then what you're going to get is a lot of things on both sides. You say, okay, how do I choose all the different constants so that everything bounces out just right? As you can tell, it might take a while, which is why we're only going to give the form. We're not going to actually solve. But, okay, good. And at this point, the book says, this takes too long. So they said, let's pull out the next method. Variation of parameters. This is fun. All right, so here we go. The other method we could do. So for variation of parameters, we can start with e to the at. Now, as a reminder from our discussion last time, this is this phi of t, phi inverse of 0. And it's very helpful to talk about what this e to the at looks like. So in particular, if I look at e to the at, the key here in our discussion for the next little bit is when you look at this, it has some columns, x1t, x2t, so forth and so on, all the way to xn of t. And these columns here, these are the solutions of x prime equals ax. And that's what we got out of e to the at. So it's how we can find our solutions to x prime equals ax. In other words, this is like the homogeneous part. So that's why we care about e to the at, is it's storing the homogeneous solutions. Okay. Now, what do? Well, we say, let's make our particular solution have this kind of form. So it's e to the at times some to be determined vector u of t. And you might say, wait, is that really what we should be doing? Well, if I think of the vector u of t, if I think of this as a vector, I have my function g1 of t down to un of t, then what happens is if you think about e to the at, which is this matrix, times this vector u of t, you're really doing combinations of your functions. So you have x1 of t times u1 of t plus dot 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 plus xn of t un of t. Whoops, ran out of space on the side. But this is where we started when we talked about variation of parameters before. So it's the same setup when we talked about variation parameters in our old normal differential equation setting. All right, great. So now, say, okay, if that's what we think it should be, we just have to figure out what u is. All right, how bad could that be? Well, we'll start and say, let's take our guess and plug it into the differential equation. So some parts are pretty straightforward. We have a times x plus f of t, and we replace our x by this form, e to the at u of t. More interesting is take the derivative. Now, here, when we take the derivative, we have a product. What rule should we use? Product rule. So you take the derivative of the first times the second plus the first times the derivative of the second. And it says, hey, e to the at, if you take the derivative of that, is a e to the at. And you're like, yeah, of course it is, Steve, come on. Just say it out loud. But you think about it, wait, that's true if a was a number. Is it still true if a is a matrix? Well, I say it is, but should we check? Spoiler alert, we're going to check whether you want to or not. So, all right, so it's still true. So let's just remind ourselves what e to the at looks like. So it looks like the identity plus you can take t times a, t squared over 2 factorial a squared, t cubed over 3 factorial a cubed. I'll even write the next term down, t to the fourth over 4 factorial a to the fourth, dot, dot, dot. So that's just what does e to the at look like. That's the definition. Now take the derivative of both sides. So what's the derivative of the identity matrix? 0. Why? Because it's a constant. There's nothing changing. There's no t attached to it. How about the derivative of t times a? A. Derivative of t squared over 2 factorial times a squared. Become t times a squared. T cubed over 3 factorial, the derivative of that times a cubed is a constant. Be t squared over 2 factorial. Now, if you're wondering how does that work, the 3 comes down, and 3 factorial really means 1 times 2 times 3. So the 3's at the end cancel, and you still have 1 times 2. That's why it's 2 factorial. A cubed How about the derivative of t to the fourth over 4 factorial? Yeah, t cubed over 3 factorial. The 4 comes down, cancels with the 4 on the end, so you still have 3 factorial left downstairs, a to the 4th. Well, what do all these have in common? Well, they look very similar to the top, but I claim they all have something in common, so I could pull it out. They all have a in it. So then you have the identity, t times a, t squared over 2 factorial times a squared, t cubed over 3 factorial, a cubed, and so forth, which makes this a e to the at. So that works. It's beautiful. It's almost like it was meant to be. In some sense, it feels like it is. It really was. Exponential functions are great. We love them. Okay, so that's how we have the derivative of e to the at is a e to the at times u of t, e to the at u prime of t. So that's part rule. And now, if you stare, and not too long, you'll notice, what do you see? We see two things are the same, and so we get cancellation. And so we're like, wow, we're close. So we're down to just one piece with the u prime. How do I get rid of the e to the at? Yeah, you move to the other side. Now, this is a matrix, so we don't necessarily divide by it. What do? We use the inverse of it. And now, the challenge, what is the inverse? Well, here's a really cool fact. E to the at inverse is e to the minus at. Really simple, slick. Now you might say, why is that? Well, here's an example. So remember, we can write A for most matrices, not everything, but for most. We can write it as B, where this comes from the vectors, this diagonal matrix with the eigenvalues, B inverse. So minus A would be very similar. You just put minuses on the diagonal. So when you take e to the at, you do the exponential e to the alpha t, e to the beta t on the diagonal. Here it'd be e to the minus alpha t, e to the minus beta t. And now we check. E to the at times e to the minus at. So we're going to copy those down. And then we start saying, oh, b inverse times b, identity. Perfect. So that goes away. Then we have e to the alpha t, e to the beta t on the diagonal, e to the minus alpha t, e to the minus beta t on the diagonal. Now, how do you multiply diagonal matrices? Yeah, you just multiply the diagonals, term by term. Diagonal matrices are really cool to multiply. That's why we like working with diagonal matrices. E to the alpha t times e to the minus alpha t. We would e to the 0, which is 1. E to the beta t, e to the minus beta t, 1. So this becomes the identity. So again, we pull it out. Now we're just down to these two pieces, b inverse. But that's the identity, and therefore, aha, it works. Wow, cool, cool. Okay, so we've moved the e to the at across, so we get u prime, e to the minus at, f of t. And now we're like, wow, we're in our home stretch. We have our derivative. So we integrate. And if we integrate, we get u. U of t is the integral of e to the minus at, f of t, dt. And we talked about how to take a derivative, but we haven't talked about how to do integration. But the moral is, it's the same idea. Entry by entry. We do it entry-wise. Now, if we're doing integration, normally when we have an indefinite integral, what should we put on the end? Plus c. So we should have a plus c here. But what is this c? What kind of object is this? Right, this is a vector. And the key here is that, we have a vector. And this is also actually a vector. So one thing you can say is it's a vector which is constant. You could also describe it, it's a vector of constants is the best way to describe it, or a constant vector. Okay, so now what's the good news? Well, the good news is we have u of t. We found it. So we can plug it back in for u of t. And that gives us our particular solution. So our particular solution is e to the at times this integral, e to the minus at f of t dt. All right, cool. Now, if we were to do an example, we would probably need about 1.5 classes. Because we know, just find e to the minus at, that takes like a half a class. Doing the integral might take us another 15, 20 minutes. Then we have to multiply that out. But it can be done. And computers, they love this kind of stuff. I want to do a little quick callback to something we saw early on. Week 1 of the semester. Oh, that's a long time ago. All right, so we're just going to plain old functions, numbers, nothing fancy. X prime equals a times x plus f of t. This is where we started with, way back when. Suppose we wanted to solve this for x. What would we do? Do what?
Subtract f of t.
Well, we probably want to subtract f of t, but this would be a subtract ax. Do you recognize, we actually had a name for this.
Linear.
Yeah, this is a linear first order. Linear, you're like, whoa, I've heard linear before. Okay, we've used linear today in our discussion. What comes next? Integrating factor. Okay, so the integrating factor, you take the coefficient here, and you take e to the integral of that coefficient dt. Oh, what's the integral of minus a dt? Minus at. Okay, so that says the integrating factor is e to the minus at. So if you multiply both sides by e to the minus at, what you'll discover is that you have e to the minus at x, and that's the, take the derivative of that, that's the left-hand side, would be e to the minus at f of t. Now, our goal is to solve for x. What comes next? Integrate both sides. All right. So we'll now integrate both sides. And we'd have e to the minus at times x is the integral. E to the minus at f of t dt. And our goal is to solve for x. We're almost there. What's the last thing for us to do? Multiply both sides by e to the at. So x is e to the at integral e to the minus at f of t dt. And now you stare at these two formulas and you're like, whoa, look how far we've come. At the beginning of the semester, we were using lowercase letters. Now we're to uppercase letters. Just think where we'll be at the end of the semester. Double uppercase. So, who knows? Who knows? But in some sense, this says, hey, these are the same ideas, the same processes. And it's just there's this extra layer that comes in that we have to remember. All right, well, I do want to work through a little bit more. We're going to switch gears, though. So that was our non-homogeneous part. We will see a little bit more non-homogeneous, don't worry. But first off, a callback. I think for the last maybe 6 lectures or so, we've been so focused on talking about how we solve these systems of differential equations, we've kind of forgotten to mention that, hey, there's a reason we care about these things. We care about differential equations because they help us to model something. They help us answer real-world situations. And not just like how many watermelons did you buy. You know, we can use this to model how things are changing. And so you might remember that the first day we talked about systems, we talked about a problem similar to this. So now that we have all our technology, I want to come back to this problem. Well, this is actually slightly different than the one we had before. So here we go. So 2 tanks with well-mixed brine, so recall brine just means salt water, are connected and they have fluid moving. And before we get into that, the punchline is we're going to let x1 be how much salt there is in tank 1, x2 how much salt there is in tank 2, and we're going to set up the initial value problem of the ODEs that model this. So we're going to use our system of differential equations to explain what's going on. Okay, so here we go. We have 2 tanks. So we're going to use our art skills here, and we'll draw a tank. We'll call this tank 1, and then we'll draw another tank, and we'll call this tank 2. And you can see from the picture, it's clear that these are tanks because it says it. So very easy to follow along. All right, so here we go. Tank 1 has 180 gallons of brine, so we're going to write 180 gallons. And initially it has 55 pounds of salt. So since x1 is the amount of salt, so initially to say 55 pounds of salt, we would say that x1 of 0 is 55. Pure water is being pumped in at 12 gallons per minute. So we have something coming into our tank. This comes in at 12 gallons per minute. And it's pure water. How much salt is in there? 0. That's like Ames water. No salt in it. Beautiful, beautiful water. All right. So brine is being emptied out of the tank at 6 gallons per minute. Okay, so there's something that's coming out at 6 gallons per minute. And brine is being pumped from tank 1 into tank 2 at 12 gallons per minute. So these tanks are connected, and we're going this way at 12 gallons per minute. All right, so that's the information associated with tank 1. Now we switch to tank 2. This has 120 gallons of brine, so it's a little smaller, but that's okay. You know, size doesn't always matter. There's initially 90 pounds of salt. What does that mean?
X2 of 0.
Yeah, x2 of 0 is 90. Good. Brine with 1 pound of salt per gallon is being pumped in at 8 gallons per minute. So there's something coming in. It's coming in at 8 gallons per minute. That's the brine. How much salt is coming in? Yeah, because there's 1 pound per gallon, 8 gallons. So this is 8 pounds per minute of salt. What else do we have? Brine is being emptied out of the tank at 14 gallons per minute. So there's stuff leaving here at 14 gallons per minute. And brine is being pumped from tank 2 into tank 1. So we're going in this direction at 6 gallons per minute. All right, so fluid is coming into both tanks. It's different fluid on the 2 different tanks. Fluid is leaving both tanks. Fluid is being exchanged between the tanks. So that's the setup. That's the setup. All right, any questions on how we got the picture? All right. Well, so now our goal is, remember, we want to set up the initial value problem for this ODE system. So in particular, when we're thinking about differential equations, we're thinking about change. So let's talk about change. So that means derivative. So whenever you think about change, change is derivative. How much is something changing? So x1 prime. So x1 prime says, let's look at how much salt there is in tank 1 and see how it's changing. So salt can either come in or it can go out. So let's look at tank 1. There are 2, do you want to do in or out first? In. Okay, all right. Yeah, 1 tank we're in. and the next tank will be out. Okay, so there's two ways liquid is coming in. How much salt is coming in from the water here? 0, okay. How much salt is coming in here? So how much is that? 6 times what? So how can I write that in a nice way? 6x2? Is it 6x2? Is it 6x2 over 120? Well, think of it this way. So right now there's 120 gallons in tank 2. 6 of them are coming over here. So we could say 6 over 120, which is 1/20th of everything in tank 2, moves into tank 1. So 1/26 divided by 120. So 1/20th of everything in tank 2 is moving over. So how much of the salt is moving over? It's not meant to be a trick question. 1/20th. Yeah, if 1/20th of everything moves over, well, salt is part of everything. The nice thing about everything is it includes everything. So we can say that the inflow is 1/20th of what's in X2. Okay, how about what leaves? Well, there's 2 places we're leaving. We're going out, being drained, and then we're moving into tank 2. Do I really need to differentiate these 2? No, because in both cases it's just leaving. How much total is leaving? 18 gallons. So how much does that translate into salt? What? 1/10. Right? Because there's 180 gallons total. 18 of the 180 is leaving, so that means 1/10 of everything is leaving. So that includes 1/10 of the salt. And because it's leaving, it's a minus sign. All right, are we good with X1? All right, next up, X2. X2 prime. Okay, well, what's coming in? We have 2 inflows. Which one do you want to tackle first? The 12? Okay, how much salt is coming from tank 1? Well, we have 12 gallons out of 180. 1/15. So 1/15 of tank 1 is going into tank 2. So 1/15 of what's in tank 1 moves into tank 2. So that's the salt coming from that part. What else do we have? Plus 8. And it's just straight up, just the number 8. Just 8. Yeah, 8. Okay. Yeah, that's fine. No problem. Okay, so that takes care of the in. How much leaves? There's a total of 20 gallons leaving. So in terms of the salt, what does that translate into? 1/6. But it's not plus because it's leaving, it's minus. So minus 1/6 X2. Now, if we were to write that in a slightly different way, we could say, well, this is minus 1/10 X1 plus 1/20th X2. And just putting it in order, X1 first, X2 second. 1/15 X1 minus 1/6 X2 and plus 8. As a matrix, since we should learn to say, go from a system to a matrix, we'd have our derivatives, x prime equals something x. What goes in here? Coefficients. These numbers. Minus 1/10, 1/20, 1/15, minus 1/6. What else do we need? This 8. So that would be separate, and we would write it as plus 0.8. So this part is the part we actually would talk about today. What is it in terms of our language today? This is non-homogeneous part. Okay, anything else we should write down for this system? Initial value, because it's an initial value problem. What is x of 0? 55, 90. Okay, so that is the answer. It asks us to set up. It doesn't ask us to solve. So this is just a reminder that, you know, these systems of differential equations, you can model things. Now we have the tools to potentially solve this problem. So we could talk about, well, how much is happening in tank 1? You know, does that amount of salt go up over time? Does it go down over time? What happens in the long run? What happens in the other tank? Which tank is going to have more salt in the long run? You know, if we were able to solve that, that would be great. Well, in our remaining time, though, let's look at a different problem. Let's solve the following ODE system. So x prime minus 1/10, 1/20, 1/15, minus 1/6 x plus 0.8 with some initial conditions x of 0 equals 5590. All right. Well, that's an interesting problem. Okay. Now, normally we'd spend probably the first 20 minutes slowly going through and finding the eigenvalues and eigenvectors, because that's the first thing you want to do with these. You know, focus on the non-homogeneous part, get those eigenvalues and eigenvectors. But they're going to be nice to us. They're just going to say, here you go. This is the eigenvalue. Here's its eigenvector. Here's that other eigenvalue. Here's that other eigenvector. Now, if you were skeptical, what could you do? Yeah, you could plug it in. You wouldn't want to like, I don't trust you. I'm starting from scratch. You know, it's instead you'd be like, let me just check. So which one should we check? Let's check one of these really quickly. Which one? 3, 2? All right. So the way you check is you take the matrix, and we have the matrix. It's just right there waiting for us. We multiply it by 3, 2. Minus 3/10, and then it'd be 2/20. 2/20, also known as 1/10. And then here, 3/15. 3/15, also known as 1/5. Minus 2/6, minus 1/3. So minus 3/10 plus 1/10, what would that be? Minus 2/10, minus 1/5. Now this one's a little harder to do in your head. 1/5 minus 1/3 is what? Negative 2/15. Yeah, you're right, because it's 3/15 minus 5/15, so it's negative 2/15. And now you just check. If I multiply 3 by negative 1/15, what happens? Negative 1/5. Multiply 2 by negative 1/15, you get 2/15. So yeah, they didn't lie to us. They actually gave it to us. Wow, good for them. Good for them. All right. Now what does that tell us? It tells us that we actually know a lot. It says our answer will have some pieces that look like this. Some constant, e to the minus t over 15. So this comes from the eigenvalue, times the vector 3, 2, plus some other constant, e to the minus t over 5, times our other eigenvector, 1, negative 2. And then is there going to be anything else? Well, there's definitely plenty of space here. A suspicious amount of space, people might say. Or no, Steve, it's just paper. Is there anything else that needs to be here? Yeah, there's a particular solution. So this is going to be our XP. See, before today, we wouldn't know how to do it. But today, we learned. All right, so let's talk about our particular solution. And the initial conditions have nothing to do with the particular solution. So we look at this and say, okay, what should our particular solution look like? Well, what's our function here? 1. 1's our function. Does that overlap with anything in the homogeneous part? No, because our homogeneous part looks like e to the minus t over 15 and e to the minus t over 5. So that says that our particular solution is going to look like 1 times some vector, well, AB. So that's what our particular solution looks like. So this is method of undetermined coefficients. Okay, that doesn't sound so bad because it's not going to be bad. What's the derivative of this? 0. And how do we know the derivative of this is 0? Yeah, there's constants. There's no t involved. So what we have is that 0, 0 is minus 1/10, 1/20, 1/15, minus 1/6, AB plus 0, 8. So let's write down these formulas here. This first one, because there's really, think of it as 2 entries or 2 lines. Minus 1/10 A plus 1/20 B plus 0. So, right, so that's where the minus 1/10 A plus 1/20 B is. Plus 0 equals 0. Now, before we go to the second line, let's just follow this one through. Let's clean it up. If we get rid of fractions, well, how could we get rid of fractions? Multiply by 20. Minus 2A plus B equals 0. What does that tell us about A and B? Sorry, what? B equals 2A. All right, so that's a relationship. And that's just from the first equation. Now the second equation, we'll have 1/15 A minus 1/6 B plus 8 equals 0. So if that plus 8 equals 0, I could just say this equals negative 8. Let's clear out our fractions. What should we multiply here by? $30. So we'd have 2A minus 5B equals minus 240. But we know B is 2A. So 2A subtract 5 times 2A would give us what? Negative 8A equals negative 240. So what does that say about A? A is what? A is positive 30. What does it tell us about B? 60. So our particular solution is 30, 60. All right. Now are we done? No. What? What are we missing? You're right. We have to take into account our initial conditions. Okay, so x of 0. Well, the nice thing about e to 0 is it's 0. So it's some constant c1, 3, 2. Some constant c2, 1 minus 2, plus 30, 60, has to give us 55, 90. All right. Well, the first equation really says 3c1 plus c2 plus 30 equals 55. So equals 25. Now the second equation says 2c1 minus 2c2 has to be 30. I'll just, in the interest of confusing you, no, in the interest of time, I'll write that, but I'll divide automatically by 2. C1 minus C2 equals 15. Now, what can we do with these two equations? Add them. If we add, what do we come to? 4C1 equals 40, so C1 equals 10. What is C2? C2 has to be negative 5. So our final answer is we end up with 10, e to the minus t over 15, 3, 2, minus 5, e to the minus t over 5, 1 minus 2, plus 30, 60. And so we can solve. On a quick final question. In the long run, how much salt will be in tank 1? Let time head off towards infinity. How much salt ends up in tank 1? 30. Because e to a large negative number gets small, so in the long run, those terms drop away. it actually doesn't matter how much salt there is to begin with in the tanks. In the long run, tank 1 will always head to 30. Tank 2 will always head to 60. So tank 1 always will have about half as much salt in the long run as tank 2. All right, that's it for today. Thanks for coming.